All right. Waited the customary 5 minutes, well, almost 5 minutes. So I will get started um, so that those who couldn't make it today will be able to watch the recording. Today I'll be covering lesson two from the stay-at-home lessons for the aerospace month. And again, for STEM Club, we offer the virtual sessions led by my USC students. They lead the virtual session for kids at the schools or kids at their home, depending on the layout of that particular school. And then we offer these professional developments for the follow-up lesson. So I usually choose a lesson and go over, so teachers that don't have experience in doing these types of lessons will be able to lead them as well. Now, we call them lesson plans, but they're not lesson plans per se because they're not part of a curriculum or framework. They're lessons on how to teach this particular activity. So I just want to make that distinction there. So hello, welcome,
Hello.
welcome, welcome. I was just getting started. I didn't know if anybody was going to come, so I recorded it anyway. I will be going through the lesson and then demonstrating how to build the lesson. So and again, it'll be put on our website for anybody who wants to watch it.
Okay.
So with that,
Thank
I shall begin. All right. So I'll look off at my. Actually, I'm going to move this over so I can look at the camera while I'm looking here. Otherwise, I'll be looking off to the side. All right. Do you see the lesson in front of you, straw rockets?
Yes.
All right, perfect. Okay, so again, this is one of the lessons, and the USC student leads the virtual session, and these are the follow-up lessons for schools that want to lead lessons with the kids, on the same theme. And this one, we're covering aerospace engineering. It'll be related to what we did last month, physics. And so I'll do a brief overview of the physics, but the in-depth one is on the recording from last week. So the students will learn about the scientific method and how it's used to build robots. And they'll also expand their knowledge about the Newton laws of motions and laws of motion, effects of gravity, and forces of flight. We're going to focus on rockets, how they're built, how they work, and how to use the scientific method. And then those are the lesson objectives. So everyone should have this. This is the lesson timing. It doesn't necessarily match that. We're probably not going to take that much time here, but you can take as much time as you want depending upon the level of the students. Materials, you'll need white paper. It says here 2 per student, or color paper, 2 per student, and that's so that the students have an opportunity to change their designs. You need scissors, tape, straw. You don't necessarily need a tape measure. You just need a way in which students can measure how far their rockets fly. So I know in some classrooms you have the little squares and each square is a foot, so you can do it that way. There's some teacher prep recommendations to read through the lesson, then practice building. There's some YouTube video links. So when we start the lesson, we want to get the kids engaged. Now, the cool thing about rockets is they're exciting on their own, so you don't really have to get the kids too engaged. They're already pretty excited about doing rockets. But we do want to get some background knowledge. We want to find out, has anyone seen a rocket before? Some kids may have launched rockets before, either the model rockets or balloon rockets or stomp rockets, or they may have seen them on television. And the question then is, how do they fly through the air? What makes a rocket fly? And then you ask the kids and they'll give you various answers. We don't say, yes, that's wrong, no, that's wrong, yes, wrong. We typically just take their answers What I've done and sometimes is I just record them on a board. Back in my day, it was chalkboards, but I guess they're dry erase boards. But I just record it, and then at the end of the lesson, we kind of go back through and see what people's ideas were. So the goal isn't here for the kids to get it right or to correct them. The goal here is for them just to put forth their ideas about how they think rockets fly. And you get some fascinating answers sometimes when you ask kids a question. You can show them different examples of rockets. Here are some here, they're different rockets, or you can download some or show some download pictures and show them on the screen or have them look on their computers. But you want to get them to see different types of rockets. And so we're going to go back to the Newton laws of motion. Now, some of the kids may have been in your lesson for October, so they may remember them, but we always like to review. If you need to go in more depth for the kids who haven't heard of it, then you can do so. But let's start here. The Newton's first law of motion says that an object at rest will stay at rest, and an object in motion will stay in motion unless outside forces act upon them. So essentially, if there's something sitting there, it'll keep sitting there unless something happens to it. You push it, wind blows, or something moves it. But the one about something in motion staying in motion unless the force acts upon it, that sometimes gets kids because they know that if they throw a ball, it's going to stop somewhere. And so when you throw a ball, part of the force that acts upon it is the drag or the resistance in air, and also when it hits the ground and rolls, friction. So those are forces that are acting to stop the ball from being thrown. So if you were to head up to the International Space Station and launch a ball from there, it would just keep going, assuming that the other planets around are attracting it due to gravity. But if you're launching it, it would just keep going until another force acted upon it. So in our case, the rockets that we build aren't going to fly unless we blow air into the straw. So we are going to be providing the force. And in the real world, rockets typically fly because of some sort of chemical reaction or a chemical reaction either from mixing of liquids and igniting them or from igniting some sort of solid accelerant, and that produces an explosion for the most part, which we direct in one particular direction, and that pushes the rocket into to make it fly. Right, and then eventually, unless you have a sustained thrust, unless you're continuing to provide that force to the rocket will fall back down to the ground. So if you cut the engines, the rocket will cruise for a while, but at some point it would fall back to the ground because of gravity. We won't get into a lot of conversations about achieving orbit or why things can stay in orbit. That's really beyond the scope of this lesson. But some of the kids may ask about that, so you may want to be prepared to find out about the perpetual falling of orbit type of deal. Newton's second law of motion states that the greater mass an object, the more force it takes to accelerate the object. And we kind of figured that if you know, the difference between throwing a ping pong ball or a bowling ball, and we can experiment with that when we're building our rockets. We can make heavier rockets. And when I build a rocket, you get a sense of how you can do that. And the force of gravity, because you have a larger mass, the acceleration of gravity is constant, but the force pulling the object is going to be stronger for a larger mass. Okay, and then the third law of motion is for every action, there's an equal and opposite reaction. And in our experiment, we'll know that the air coming against our rocket when we blow will essentially blow right back out the back, and that causes it to move forward. We have that resistance force. If you make a really aerodynamic rocket, it'll go further than a rocket that's not as aerodynamic. One thing that I do sometimes with kids with this project is whatever size paper they use to create the rocket, I have them take other sheets of paper and see how far they can throw those sheets of paper. And so if you just take a sheet of paper and you try to throw it across the room unballed, it goes so far. Even if you ball it up, it'll go so far. And so we can see that for a given amount of force, if you can decrease the amount of resistance, then it goes further. So the action reaction for our rocket slowing down because air resistance won't happen. And then we talk about the force of gravity. Oftentimes what I do with this is I just have the kids jump up and down, not because it really teaches them about gravity, but it burns off some of that kid energy. And it's also pretty fun to do because then I get a chance to jump up and down. And then, you talk to them about, jump as high as you can. And then they will know that every time they want to jump higher, they have to use more force because the gravitational force will continue to push them down. So we need a lift force to overcome the gravitational force. And so there's more detailed explanations in the recording for last month with physics, but we just wanted to give them context. Any questions?
No, no, that now I was laughing at the I like to jump up and down and the justification behind that. Yeah,
Uh,
yeah,
I,
it
I
sounds
definitely
good. Sounds
I,
good.
I definitely like to have them do some movement. All right, so now we're going to talk about the forces that act on a rocket. There are four forces that act on a rocket. And this is just a rocket that, uh, not a blow rocket, although the forces are the same for a blow rocket, but we're talking about just the rockets that you see that lift off in space. Um, the, the force are lift, drag, weight, and thrust. And these are the four components of flight anyway. They're different for a rocket than for an airplane. Okay, so um, the lift and drag are aerodynamic forces, meaning that it has to do with how much wind resistance and that the rocket experiences. Wind resistance that causes the rocket, or in the case of an airplane to move up is called lift. And the opposing force, the wind, like if you stick your hand up the car, don't. But if you stick your hand out the car, you have that opposing force. So if you ever ride a bicycle, or even on a windy day, you feel that force against you. That is drag. And then we have weight, which is due to gravity, and then thrust. So in order for a rocket or and also an airplane to lift, and I think you'll cover this in the glider lesson, or the students will, lift has to overcome gravity and thrust has to overcome drag. So you have to push past the drag, and you can see the way that the forces are acting. That drag and thrust are in opposite directions. All right, so that's just the overall concept, and like I said, when I'm doing the lesson, what I try to do is make sure that the students have a good sense of the science behind it. You can bring additional resources for the kids to look at as well, but the goal is for them to get a sense of it, and then we start building. Now, I'm going to go through and build one of the rockets in a moment, but the goal that we're going to have is we're going to have the kids build a rocket, fly it, and then try to figure out why it went the distance that it did. So we're going to use the scientific method where they're going to create a hypothesis, say, why did my rocket go this far or not go this far? And then they're going to use the scientific method to either prove or disprove their hypothesis. And then they're going to use the engineering design process to, based on what they've learned from the scientific method, they'll use the engineering design process to actually build a better rocket. So that's sort of the way they work together. Oftentimes people think it's an either or with the scientific method and the engineering design process. With the scientific method, we're trying to get a sense of understanding, and then we use that understanding by creating hypotheses and doing some experiments and then coming up with a conclusion. Once we decide on or reach a point where we have understanding, then we can use the engineering design process to modify that design, because we're not just randomly changing things. Sometimes when you're building things with kids and it doesn't work, they'll just take the entire thing apart and rebuild it from scratch. It could have just been one thing that was wrong and their design was fundamentally solid, but they just had one thing wrong, which is why we want them to go through the scientific method, which is to change one factor at a time and then think about it. And then once they say, hey, I noticed that the weight of the rocket or the size of the fins makes a difference. Now I'm going to redesign my rocket based on what I understood. So let me switch here. All right, so I will stop sharing this here and I will go here and share my lab camera. All right, so, all right, and let me come over here. All right, so fortunately, I can't show the lesson while I'm doing it, so I will talk through it. All right, so you want to fold the paper. I need my extra papers over here. You want to fold the paper into fourths. I fold it hamburger style into fourths, because if you fold it hot dog style, the paper's too long for the straw. And even when you do it hot dog or lengthwise, I mean hamburger shortwise, it's still kind of long. Now you can actually use the entire paper if you wanted to create a heavier rocket, but we're doing this so that kids can experiment with their rockets to decide on heavier or lighter, or does it make a difference. So you fold the paper into fourths, and then you cut along the folds. I'm only going to cut 2 of these guys here. I have to remember where the camera is. All right, so I'm gonna cut this here. So I'm just gonna cut 2 of those. All right, so that's what we do, we cut. And now what we're going to do is we're gonna take the straw and roll it, and roll the paper on it. Now, you may wanna just kind of, just move, this isn't in the lesson, this is experience that I've had. You just kind of wanna, since you're gonna roll it anyway, you wanna kind of crinkle the paper, not ball it up, but just kind of roll it like this so that you can, get the fibers, make the fibers work. Now, something else that's not in the lesson that I do also is it talks about rolling the straw and then taping it. Well, what you'll see is when you roll the straw and then tape it, you have to hold the straw in pieces, and then you have to try to tape it, and then it unravels. So over the years, I've come up with a solution to that, which is I am going to put tape at the end of, let me put it here, at the end of the paper like this. So the sticky side is up, and I'm going to put the paper halfway on, halfway off. And so when I take my straw and then I roll it around it, and this isn't easy either. Sometimes, kids get frustrated because they think it should be easier. It isn't. Trying to roll this around is a bit of a challenge, but you don't want to roll it too tight, because the straw then gets stuck. And as you notice, I'm rolling. And when I roll it, because I have the tape on the end, it sticks automatically. So I'm going to show you the other way. And this is the way that the instructions say. And then my students do this because, they're young, they can, their hands are fast, but I don't work the way I used to. But when you try to roll it first like this, you're rolling. Now I've got to hold it here and then try to get the tape on here. And as you can see, you don't get it right like here. I mean, it's not impossible to do. Like I said, young people have a way of being able to get it done, but your tape gets all crooked if you don't do it right. So that's why I put the tape on the end instead and then roll it, because as I roll it, then I'm done. Now, one thing that the lesson talks about is the nose cone. It talks about pinching here to make the cone, and you can do that. And that's the easiest way to do it, particularly with younger kids. You just kind of pinch, and you end up with kind of like this piece like this, and then you can add a little bit of tape. The idea of that is to make sure that no air escapes. That's why you put that there. Now, what I've also done in the past, and this is not in the lesson, what I've done in the past is I have, where's my other paper here? I have created a cone. And the way I create a cone is I cut a small letter D like this. You can see it here is a small letter D. And then I fold the ends of it. Let me get a piece of tape first. I fold the ends of it like this. And it's not that, hey, let me turn like this. You fold the end like this and like this, and you create a cone. Create a cone like this, and you could stick that cone on top like this. Oops, you can stick that cone on top like this. So I've done that as well. I like, for the older kids, I like having them create a cone. And for a couple of reasons. One, it gives them a precursor to calculus when you're talking about rotating objects in three-dimensional space and the volume and area. I mean, I don't tell them it's calculus, but sometime later when they're in 12th grade, they'll be like, wait a minute, I did something like that when I was in elementary school. I like that part for the older kids. And also, I want them to experiment with different sizes of cones. With the younger kids, this is fine because you have to have some dexterity, as you saw that because it's a small straw racket, the letter D was really, really small. You have to have that kind of dexterity in order to fold it. So either way. And then the lesson plan talks about also creating the fins right now, but I don't usually do that right away. What I do instead is I have them try to launch the rocket with just this part. And what'll happen is because there are no fins, the rocket's gonna tumble. It'll tumble. So you can try that, just blow into the straw. And when you think about blowing it, it's like the olden days. I hate even saying it because particularly with elementary school, it's like blowing a spitball. You pressurize your mouth, put your tongue in the straw, and then move your tongue and get a big force of air. I've done that a few times at some schools where kids did not know what a spitball was. And lo and behold, all my science kids know how to do spitballs after that. And the teachers really appreciate that after that. So, but your choice. But I do like to have them blow so that they can see that it tumbles. And without the, unfortunately, my camera doesn't pan out, so you wouldn't be able to see it in real time and it would look weird anyway. So what I do then is after I have them do that, I then have them cut some triangles for the fins. Now, the lesson says to do 3 triangles. I usually have them do 3 triangles or 4 triangles. And then I talk to them about the degrees in a circle. And so, this light is really bright. The degrees in a circle. So if there are 360 degrees in a circle. And so if I have 3 fins, then they're going to be 120 degrees apart. If I have 4 fins, they're going to be 90 degrees apart. So I usually talk to them about that, have them do the 3 fins on one rocket. And then when they're building the other rockets, I have them try to build 4 fins. 3 fins is a little bit more challenging to mount because trying to estimate 160 degrees is a lot harder than trying to estimate 90 degrees. And then what I do is I have them create a small triangle first, and then I have them use that triangle to cut the additional triangle so that the triangles are all the same size. And usually about this time, I talk to them about the difference between fins and wings. So the difference between fins and wings, because kids will sometimes confuse them, is that if you look at this rocket here, the one I built earlier, these are fins. And fins do not provide lift. Fins provide stability. So what you'll notice is when you launch this rocket, it will tumble. When you launch this rocket, it has a nice parabolic or half circle path because the fins control how the aerodynamics work. The air flows over them, so it can't flip over because the air is pushing down on 2 of the fins, and one in the air is also one fin's keeping it going straight. And so by having them do both, they can see the difference between fins and no fins. But these are not wings. These do not give lift. If you have time, what you can do is you can add a wing to this, like this, and then have them launch it, at the end of the lesson. I usually curve it up a little bit to give it a little bit of lift. But this is no longer a rocket. This is a cruise missile. So when you see the Tomahawk missiles that they show on TV and everything, this is a cruise missile. This is not a rocket anymore. When you start adding wings to it, these are for lift. These are for stability. So I usually talk to the kids about that as well. And again, it's not in the lesson because we don't want to overload the kids with that. But you can look it up or you can practice it on your own. Now the next thing I do is I want to tape the fins to the back of the rocket. And the way I do that is I cut a little piece of tape here. And you can use any tape. I just happen to use the Scotch tape on this one because my masking tape isn't that sticky. And you just put the tape on one side of the fin, halfway on, halfway off, very similarly to how we did the tape halfway on, halfway off the paper. So you put it on halfway off, you fold it back, and then you just stick it right there onto your rocket. Now, the other thing that I always talk to the kids is your fin has to be straight. So you have to look down the nose. Let me see if I can get this right here. You look down, there we go. I think I got it. Yeah, you can see it. It's hard to see. If you look down the nose, you should only see the edge of the fin. If you put it on funny, it's kind of angled, then your rocket will behave in accordance with that. And then you tape down the other side. So I taped one side, bent it down, and I taped the other side. And this is a terrible job, but you get the sense of it. And then I'm going to do the same thing for the other 3 fins. But again, you can do 4 fins and teach them about angles, like 90-degree angles, or you can do 3 fins and then teach them the 120 degrees. What I tend to do is I tend to have them start off with the 120 degrees because it's a little bit more challenging, and then I have them do the 90 degrees. And usually the kids go, "This was easier. Why didn't you tell me that in the first place?" And so I added the other one there. But the other thing that happens is we talked about Newton's second law, which has to do with mass and force. If I add an additional fin, I've added additional weight, and that's mass. We have more mass. And so for the same amount of force, we won't travel the same distance because we've added weight to it. So there's a trade-off. If the additional fin makes the rocket more stable and it's able to travel further, then the cost benefit is in the favor of adding additional fin. If the additional fin does not increase the accuracy and the stability of the rocket, then you just added weight. And that's what we want kids to see. And so this is what your rocket looks like. It's a rock. This is the one that just has the bended top and the tape. It's this. You got the fins there. Again, if you wanted to, you could add the cone and then tape it on if you wanted to. And then you put a straw inside of here. And let me switch over to the other camera. And then you do this. So I will launch here. I'm not sure where's it gonna go.
All right.
And so, and then that's what you do. This is the one that I built with heavier tape earlier. They both hit the wall. My assistant's going to come in and try to figure out why she has paper straws on her desk. But that's essentially the essence of it is as we're going through, it's sort of like the way I was talking through the different parts that's how I usually do the lesson, where I'm talking to them about the different aspects of building a rocket, about the fins, about the cone. For your older kids, I would have them, do both the pinch and then have them do the cone. I would have them do the fins, the paper fins, doing 4 and then doing 3. And then I would also have them put wings on. Something that some of the kids do is they'll put 2 sets of fins on, one at the back of the rocket and then one in the middle of the rocket. That allows the rocket to fly even straighter if you align those fins perfectly. If not, then your rocket will have a little bit of instability and you just added weight, so you really haven't benefited from it. Any questions? That's pretty much it on the rocket. Oh, no, I'm sorry, before I go on. For the discussion part, you want to have the kids briefly present their rockets, talking about what they've done. Here, let me move this over here. Where am I? Sharing here. So you want to have the kids briefly, you want to have them share. You can ask them if the rockets worked or they didn't work. If it doesn't work, it's perfectly fine. We have lost many of rockets. NASA's lost many rockets, sending them out into different places. That's how we learn. And then they go through and they redesign. When they're experimenting with their rockets, like I said, they'll use the scientific method. They'll say, hey, my rocket did not work. Here is why I think it didn't work. My fins weren't on straight, or my cone, or my weight was wrong. And then you have them prove or disprove it. So you say, if your fins were on wrong, then try putting your fins in different places, different ways, and then experiment to see if the fins do have an impact on that. And then once they decide whether they do or whether they don't, then say, now that you know that fins have a major impact because of your scientific method, let's use the engineering design process to design it. They can ask their classmates how theirs work. They can compare them. sometimes what I do, and I know it's probably frowned upon nowadays, is I have little competitions to see whose rocket goes the straightest and whose rocket goes the furthest. I do both because the kids with the big lungs can make the rocket go further because they can fill up their lungs and pressurize their mouth more than the smaller kids. But going straight is the challenge. And so I usually have them do challenges that way, who can go the furthest, who can go the straightest. And then I start, adding some things like who can make their rocket spin, not something you want in astronauts. You don't want to be in there and having your rocket spinning as you're flying through. But it's just something to give them ideas. And then that's it. They keep their rockets. They clean them up. Because well, even before COVID, I always make sure that kids keep track of their straws because kids are nasty. They'll share their straws just because they're kids. So you have them keep track of their straws. You really can't mark or write on straws. And then the other thing is before they launch their rockets, have them put their name on it because the rocket that goes the furthest and the straightest is always mine. Everybody said that was mine. That's mine. So it belongs to mine. So before, especially if you're going to do a competition, tell them put your first and last initial on the rocket so that you can keep track of your rocket. So that is the extent of the rocket. Any questions?
No, this looks good. Very,
Awesome.
very nice. Thank you.
Awesome. Very cool. All right. So just let us know if you have any questions. And like I said, I'll post this. My team will probably post it sometime next week. Our web
Okay.
team. Everybody's gone for the day, and then we'll post everything. All right.
All right. All right.
All right.
Thank
Have
you.
a good one. You're welcome.
Appreciate it. You have a good one too. Thank you.
All right. Okay.
All
Bye-bye.
right. Bye.